Hello, my name is Maria. I'm a PhD student at CMU LTI, and I'm presenting our work on comparative error analysis in neural and finite state models for unsupervised character level transduction. This is joint work with Ed Hovy, Taylor Berg-Kirkpatrick, and Matt Gormley. There are many NLP tasks that can be viewed as character level transduction, for example, transliteration, grapheme to phoneme conversion, or morphological inflection. These tasks all have structural constraints like monotonic alignment, and they were traditionally modeled with finite state transducers. But recently, sequence-to-sequence models have been getting state-of-the-art results on those tasks. They are powerful and can learn the patterns from the data without explicit information about the underlying generative process. The trade-off between structure and power can be observed across different dimensions. The first one is language modeling capacity. Finite state transducers rely on the Markov assumption, so they use character-level n-gram models which are weaker than recurrent language models with unlimited left context. The second is the controllability of learning. Structured models like FST allow us to constrain what kinds of patterns we want our model to learn. Seek-to-seek models are less controllable, and they might pick up on biases orthogonal to the task, like domain imbalance. And another dimension is the search mechanism. FSTs can perform exact maximization at decoding time, but neural models decode with methods like beam search, and they are prone to errors like repetition or empty outputs. So in this work, we compare the performance of a finite state and sequence-to-sequence model on two unsupervised tasks, deciphering informal romanization and translating between closely related languages. And I'd like to emphasize that most prior work focuses on the more common supervised scenario. And here we're looking at how well the intuitions from prior work will transfer to the unsupervised case. So we perform a side-by-side error analysis to highlight the strengths and weaknesses of each model class. And additionally, we explore simple test time model combinations to see if they can leverage the strengths of the two approaches. So our first task is converting informally romanized sentences into native script for Russian, Arabic, and Kannada. Informal romanization is an idiosyncratic way to represent non-Latin script languages using Latin alphabet, and it is commonly used online. Idiosyncratic means that it's not standardized, and character substitutions are up to the user. This is why for each word here, we have multiple possible romanizations. And these substitutions are not arbitrary. Most of them are based on either phonetic similarity between character pronunciations or visual similarity between character shapes. And in the examples here, I'm highlighting some of the phonetic substitutions in blue and some visual ones in red. One structural constraint on this romanization is that the character alignment is monotonic because you want to preserve the order of the characters. But the nature of the alignment also depends on the writing system of the language. It is mostly one-to-one, but there can be null alignments for things like omitted vowels or one-to-many alignments for characters representing entire syllables. Our second task is translating between closely related languages, in our case, Serbian and Bosnian. Serbian and Bosnian are so close that they have a nearly character level correspondence. They're also written in different scripts, so we're again framing the task as an orthography conversion problem. And the transliteration framing of translation is inherently limited because the task is not truly character level in nature. You can have non-cognate translations or paraphrasing, like here with the word education and teaching. And here the paraphrasing leads to even more discrepancies because of morphological agreement. We have a neuter noun on one side and feminine on the other side, so the adjectives agreeing with these nouns will have different endings. And now I'll describe a finite state model, which we've introduced in our prior work. It's a classic noisy channel decipherment approach where we decompose the marginal likelihood of the sequence into emission and transition probabilities, very similar to an HMM. And we approximate the latent character alignment using insertions and deletions, which correspond to an empty character epsilon on the latent and the observed sides, respectively. We introduce the inductive bias into our finite state model through priors on emission parameters. Like I said, people usually substitute characters with ones that are visually or phonetically similar. So we collect pairs of similar characters from resources like phonetic keyboard layouts and Unicode confusables list. Our finite state model is a cascade of two components. The first one is the transition model. That's a 6-gram character language model of the native script. And the second part is the emission model. This model has args for all substitutions, insertions, and deletions. And an important detail about this transducer is that it has a limited delay of all paths. So delay is the difference between the number of insertions and the number of deletions at each time step. You can think of it as restricting the distance from the diagonal in the alignment matrix. We train the model using hard EM algorithm, and we compute all the necessary statistics using finite state methods, for which we use the OpenFST toolkit. This computation is quite slow, so we use a stochastic training procedure. And importantly, we only train on a subset of the available training data, because this method converges before we do a full pass over the training set. Our sequence-to-sequence model is the unsupervised neural machine translation model of Lampel et al. It maps both the source and target sequences to a latent space, and it's trained to denoise and reconstruct sequences, perform back translation, and discriminate between sentences from different domains. We're using the probabilistic formulation of this approach introduced by Jun-Chin He and colleagues. And we're also going to explore some model combinations. The easiest way to combine two separately trained models is re-ranking, where one model generates its top K list of most likely candidates, and then the other model scores them and chooses the best one. Our second approach is product of experts. Here we perform beam search on the FST lattice, and each possible next output symbol is reweighted by its probability under the sequence-to-sequence model at the corresponding time step. Insertions and deletions cause some complications here. Deletions or empty outputs don't correspond to anything on the seq-to-seq side, so we can't reweight them. And insertions correspond to empty inputs. And because of them, we can't group hypotheses on the beam by the length like we usually do. Instead, we group them by the length of the input sequence portion that's been consumed so far. So we train the models separately and then combine them at test time. Now let me introduce the data. For Arabic romanization, we use the LDC Bolt dataset, which consists of SMS and chat dialogues between Egyptian Arabic speakers. The messages are written in Romanized Arabic or Arabizi and converted to Arabic script. For Kannada, we use the Dakshina dataset. Unlike Arabic, here the texts are originally in the Kannada script. They're taken from Kannada Wikipedia, and the romanizations are then elicited from native speakers. For Russian, we use the dataset that we collected in our prior work. It consists of romanized comments from a Russian social network, vk.com. For the native script side, we use a portion of the Taiga corpus that's also scraped from the same platform, but mostly from the political discussion groups. And for the translation task, we use the monolingual Serbian and Bosnian data from the Leipzig corpora. We need parallel data for validation, so we use the synthetic parallel validation set of Yang et al., which is also Leipzig corpora data passed through Google Translate. But we want to test on natural parallel data. So as our test set, we use the Universal Declaration of Human Rights. So now let me show the results for the romanization. But first, I wanted to show a disclaimer and say that this isn't an abstract fair comparison of the unsupervised FST and the unsupervised seq-to-seq, because they're trained on different amounts of data. FST was too slow to be trained on all available data, and the seq-to-seq didn't work if we trained it only on a small subset of the data. So we're just looking at how to best leverage the strength of the two approaches. So this graph shows character error rate, so lower is better. And on character level, FST is doing better for all three languages, again, despite having less training data. The model combinations have different levels of effectiveness, but mostly they're just kind of in between the scores of the two base models. So instead of bringing their strengths together, they just kind of interpolate between the behaviors of the base models. Re-ranked FST actually performs a tiny bit better than the base FST, and a product of experts also helps in one case. Here we're showing word error rate. So again, lower is better. Here we have the opposite picture. Unsupervised seq-to-seq is better than FST on word level, except for Kannada for some reason. Model combinations are again scoring mostly in between, and re-ranking either helps a little or at least doesn't make it worse. And finally, another word level metric, blue. Here, higher is better. And again, the observations are similar to what we just saw for word error rate. Unsupervised seek-to-seek outperforms unsupervised FST for Arabic and Russian, but not Kannada. And again, re-ranking occasionally helps a little. I'll skip most of the translation results because the observations are similar and you can find the numbers in the paper. I just wanted to highlight that here we have one additional point of comparison. We've trained the same unsupervised sequence-to-sequence model with subword tokenization, which is what prior work uses. And the character level seek-to-seek is much better on all three metrics. This suggests that character level tokenization itself can be a useful inductive bias, even for tasks that aren't truly character level in nature. Now let's look at some of the actual outputs. Here I'm showing an example from the translation task. We've seen that the FST is better on character level and seek-to-seek is better on word level. And here's what it looks like. FST predicts the right words, but introduces character level noise into a lot of them. And seek-to-seek is good at reconstructing whole words, but then it just deletes several words from the input. And re-ranking the seek-to-seek with the FST actually gets rid of the deletion, and the output is as close to correct as possible. The parts highlighted in yellow don't match the reference only because of paraphrasing. So the model actually transliterates correctly, but gets penalized for our task not being fully character level in nature. And this is the subword model. This just hallucinates most of its output. And I wanted to finish with some high-level takeaways, illustrating with examples from Russian romanization. And first of all, we were hoping that model combinations would get rid of seek-to-seek issues like deletions or hallucinations. And they do somewhat, but not completely, which is why their scores are in between the two base models. And at least for re-ranking, the issue is beam search. I'm going to illustrate this with an example. Here I'm showing the romanized input, the Cyrillic output, and the rough English translation of the sentence. And these are the final hypotheses under the neural model in the re-ranker scores. So what happens here? Seek-to-seek hallucinates something early in the sentence because the language model gets immediately distracted by the first character in the input. So instead of the word this, it predicts United Russia, a name of a political party, which has absolutely nothing to do with the rest of the sentence. And then the seek-to-seek comes back on track and predicts the rest correctly for as long as we allow it to go on, but that's not good enough. The re-ranker can no longer help here because the hallucination made its way into every hypothesis on the beam. So we need either a much larger beam size or a diversity promoting search mechanism. So how did this become United Russia in the previous example? Remember that our Cyrillic data comes from political discussion groups. So names of political parties and politicians are disproportionately common on the native script side. The seek-to-seek language model gets distracted by the first character of the Romanized sequence and just goes on to generate what it memorized. And in fact, 25% of the most common word level errors under the seek-to-seek are of this type, compared to just 3% for the FST. And finally, the FST errors are more repetitive. Here you can see the most populated fragments of the character level confusion matrices for the two base models. And you can see that the left one corresponding to the FST is notably sparser. And for example, instead of the letter ya, the FST most often predicts a, and the other substitutions are rare compared to that. But for the seek-to-seek, the error distribution for ya is much closer to uniform, although errors involving predicting relevant characters are a little bit more likely than the rest. And since the errors of the finite-state model are more repetitive, they might be easier to correct with some kind of rule-based post-processing. And I wanted to conclude with some discussion of future work. Like I said before, there is a trade-off between power and structure, and our neural models are getting more and more powerful. It has been recently shown that transformers can perform character-level transduction without a need for explicitly encoded structure. But this result was obtained in a supervised case, and in unsupervised or low data scenarios, encoding structure is likely to be crucial. So I still think that combining the unsupervised finite-state and neural models is the right way forward. We didn't really get any good result from our simple test time combinations, but there are other ways to do it. Like we could try the same kind of joint decoding at training time so the models can learn from each other. We could structurally integrate the desired properties of one model into the other, or try to bias one model towards behaving like the other. And that's all that I wanted to say today. Thank you for watching. This is the link to the paper, and please feel free to reach out to me with any comments or suggestions.